Object recognition, just to clarify, the nomenclature can be a little confusing. In general, we can deal with different tasks. We can have image classification, pretty simple. It's a binary classification, so you have an image and you just want to know, you want to know whether objects belonging to certain classes are present or not in your image. Then going a step further, you have object detection, which is what I'm going to focus the most in this presentation. Basically, you don't only want to know if an object is present, if an object from a certain class is present in your image, but you also want to know the location of the object. Localization, which takes place, which is achieved by the use of bounding boxes. Well, the name is self-explanatory. So you locate the object, but you are not really interested in separating, for example, say, the object from the background, which in turn is the purpose, is the scope, is the aim of other more advanced techniques, where basically you want an object detection which is with a pixel level precision. So you are interested in separating the precise boundaries of different objects. And even in this case, you can separate between methods which separate many instances of the same class or not. But again, I'm going to focus on these methods in general. Okay, as you can imagine, we need metrics to evaluate the performances. There are two problems. So we have to evaluate both the precision of the localization, which is, and the classification precision, of course. Now, the localization is measured, is evaluated by the use in general of the intersection over union. Again, it's self-explanatory, but you have your predicted grounded box, the true one, the ground truth. So basically, you evaluate the ratio between the area of overlap, or so how well they match, and the total area. And in general, you set a threshold and you discard detections that don't meet this threshold. While for the accuracy of the classification, I can go more in the details later if you want, but in general, you have your precision recall curve for the classificator. You calculate first an average precision for each class for different values of the recall, and then you average everything over the many classes that you are considering. So in general, if you look at papers in this area, you have this quantity, and in general, it's always referred to the value of the IOU that you're assuming. So you can imagine that if you set a stricter constraint on how well you have to localize the object, the overall accuracy is affected as well. Okay, so in general, I decided to focus on two families of models, which are at two opposite extremes, basically. On one end, you have region-based object detectors. They are the most accurate ones, and they are slowest. The idea in this case is that the whole process takes place in two following steps. So first, you use generally external methods to locate the so-called regions of interest. So basically, you locate areas of the image where you expect the object to be located, and then you classify them. On the other end, you have faster methods, single-shot detectors, which, however, are characterized by a worse accuracy in general. So the main ingredient of region-based detectors is, again, the localization of objects. And you can do it in, let's say, two ways, mainly. You can use external methods like the selective search. And I'm going to tell you something more about the second method later. In selective search, you have your image and you proceed hierarchically. So basically, you start from the single pixels and you start grouping them together according to their similarity. The similarity is evaluated based on color, shape, and other parameters. And there are a few precautions that you take. In general, you try to avoid bigger clumps of pixels from swallowing the whole image, so you favor the smaller ones. And in general, you require a high recall from this method. So you predict lots of regions of interest, and then you filter them out in the classification phase, which is the main reason for which is why basically these methods are slower in general. And so I'm going to basically talk about one big family of these region-based detectors. The simplest one is the RCNN, region-based convolutional neural network. The workflow is simple. You have your image and you use in general an external method, so like the selective search I just told you about, to locate the regions of interest. In general, you produce many proposals in the order of thousands of them, and you feed all of them to a convolutional neural network, after which you have a fully connected layer for the actual classification and to refine the localization of the boxes. Now, the method is really accurate, but you can immediately spot the problem here. Basically, you are extracting the feature thousands of times for each image, so which makes everything incredibly slow. So a step forward, an improvement from RCNN is the fast RCNN. And if you think the name is original, wait for the next one. But in general, what you do is you have your image, you extract the features just once for the whole image, and you do the same thing than before. But so you locate the regions of interest, but you don't do it again on the image, you do it after the feature extraction. So basically you combine the feature map provided by the convolutional layer with an external method. So you locate the regions of interest in the feature map and you do the same. Again, fully connected layer for classification and refining the position. In this case, it is faster, but again, the external method, the selective search, is lower than the rest. So most of the time for each detection is actually consumed for the localization of these regions. And so you go to the faster RCNN, where basically everything is performed by convolutional neural networks. The conceptual step is simple. So you have your feature extraction and you use another convolutional neural network, so you go in parallel for creating the proposals for the regions of interest, and you end up the same way. So basically this network provides both the bounding boxes and tells you how confident you are that these boxes actually contain an object. And I will tell you something more about this network, but it's basically useless because it's more or less it's included in the second family, in the second group of detectors, which are the single-shot ones. So I'm gonna tell you something about two models, the single-shot detector and YOLO. Now, you can think of these detectors basically as a, I don't know, smarter version of a sliding window detector. So basically, you have your feature map, and you slide a window over it, looking for bounding boxes. The thing is, the main characteristic, both of the network in the previous model and of these single-shot models, is that you don't look for bounding boxes randomly. Basically, in each position, you create a set of default boxes. In general, they're called anchors, which are characterized by a wide range of dimensions, aspect ratios. So basically, you are trying to catch every possible dimensions of the object. So for each position, you have a collection of these default boxes, and you try to catch the right ones by deforming, modifying the anchors. So that's what you do in the single-shot detector. In YOLO, you do, YOLO stands for you only look once, and it's another single-shot detector. Basically, the concept is more or less the same. So you divide your image in a grid. They go separate ways in this case. Basically, each cell produces again a set of default boxes. So you calculate a score for every box, which is class independent. Then for each cell, you have a classification score, which is class dependent. You combine everything and you have your overall detection. Okay, so after this short summary, the main question that you can be wondering about, of course, is which is the best model. I'm gonna get there. And the short answer is that, of course, there isn't a best model. It all depends on what you need. So by skipping these things, the main thing is that there's a trade-off, as I told you, between the speed and accuracy. So again, it all depends on what you need. If you need real-time performance, you can mostly forget about region-based detectors, but there are a few things that you can do. For example, in this work by Google, they compared the performances of different detectors. There are a few sweet spots. So basically, there are a few detectors, real-time ones, that can provide a very good accuracy. And in general, there are other things that you can do to increase the speed of region-based detectors. Mostly, for example, you can try to decrease the number of proposals for the regions of interest. I told you, in general, you propose like thousands of them. It's not always necessary. You can play around with the convolution, with basically the feature extractors that are included in your network, which is more effective for region-based detectors. As you can see here, single-shot ones are basically unaffected by the choice of the feature extractor. Watch out for the dimension of the objects. Single-shot detectors, their accuracy drops significantly for smaller objects. So it's something else that you have to take care of. And the resolution of the image, it's something that you can really play around with, because in general, the idea is that if you decrease the resolution, you decrease both accuracy and the time you need for the detection, but in general, the accuracy is affected less. So again, it's something you have to tweak and play around with to meet your needs. And I'll stop here, I guess, and if you have questions.
Any questions? So, which of these architectures will you use in the project?
That's the thing. In general, we are going for a more or less real-time performance. So far, I've been testing mostly single-shot detectors. I'm getting weird results, so we might have to look for something else. But so far, the single-shot ones.
Okay. Any other question? No. Done. Let's thank the speaker.
Huh?
Okay. This was the last presentation in this section. So now we have a half an hour break and then come back to the next one.